All right, so people are going to be behind a little bit because I'm not able to stream this because the internet's not working. Is that showing up there? All right, so go ahead and open up that decoder that we did. Do it. Yeah. All right. What I want to talk about today, if we can get through it, is decoders, encoders, multiplexers, which we'll just call a MUX, okay, and demultiplexers, if we can get there. And if we can, we'll look at easy addition, okay. All right, so hopefully we can get to maybe half adders today. All right, so when we said that a 0101 was going to output an R, that was decoding, okay? We took binary and we made it something that meant something to us. Now, what we did when we said an R, like the abstraction R, was equal to 0101. Wait, that's not what we said it was. It was 0001, 0001, right? We said that an R, you know, that is going to be represented by a 0001 in our little thing. That was encoding. Okay. Did y'all read about the encoder and the decoders? All right. So, let's make an encoder. Okay. All right. Before I start throwing stuff down in deeds, I need to know what I want it to do. Right. Now, there's a chart where it's a decimal to binary encoder. Right. We've done a binary to decimal encoder before, where we were like, okay, for 0, if it was 000, that means we need an inverter, and an inverter to make those ones, and then we pump that into an AND gate, right? And then we had a little LED sitting out there. It's an LED, and that would turn on, you know, a light by the number 1. Okay. All right. So we need to kind of go the opposite direction a little bit. Okay. We're going to make an encoder. All right. So they did one for 0 through 9, and they needed 4 bits to do that, right? Because 9, 8, and 9, you can't get into 3 bits. I don't want to do that many right now. So let's go 0, 1, 2, 3. How many bits can we get in those into? 2, right? All right. So then we've got 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now, when we do a truth table, it doesn't matter how many outputs we've got. Okay. We can make a separate truth table for them, but like y'all should know, just deal with one column at a time. Okay. So we'll say this is an LED right here and an LED right here. So if we push it in number 0, neither one of those lights should come on, right? Right. All right. Then what we do is let's say we have a button. It's a 0 button. It's not tied to anything. 0 doesn't turn on anything. Then we've got a 1 button, and we want it to turn on. Let's call this Y and Z. Okay. We want it to turn on Z. All right. All right. Number 2. We want it to turn on Y. And the 3rd button, or really the 4th button, we want it to turn on Z and Y. All right, now work your way backwards, okay? When is Z on? If 1 or 3 is pushed, right? It's going to be your Z output. Y'all cool? When is Y going to be on? 2 or 3? That's an encoder. I push the 0 button, neither one of those lights come on. I push the 1 button, Z comes on. Push the 2 button, Y comes on. Push the 3 button, Y and Z come on. All right, so now like you can do that for every number and every letter, couldn't you? Okay, so let's make it a little bit more interesting. We've got 0, 0, 0, 1, or just 2 zeros for this. And we said this was going to be an R, right? 0, 1, 0, we said was going to be an O. Zero, 1, 1 was going to be a B. A hyphen was going to be 1, 0, 0. And the other B is going to be encoded as a 1, 0, 1. So what I want to do is, instead of have that counter doing, I'm making a keyboard now, right? Cool. All right, so in making a keyboard, you got to realize that this is like extra. Like this is a second B. So let's ignore it. Okay, we don't want 2 B's up there, right? we just did the second B so that it would whatever. But now we should be able to type out Rob-B, okay, with our 4 little buttons. All right, so let's call this column X, let's call this one Y, and let's call this one Z. Okay. So we've got a button that says R, and we want it to, let's work backwards. When is X on? Only on the hyphen, right? When is Y on? O and the B, right? When is Z on? R and B, okay? All right, so the X, the most significant bit, will be tied to the hyphen button. Okay? Cool. The Y is going to be tied to O or B. All right? And then Z is going to be tied to R or B. All right, now let's go into deeds. So instead of using this counter right here, we're going to delete it. Yep. All right, let's put 3 buttons, input push buttons. Okay, we're going to call this one R. We're going to call this one O. We're going to call this one B. We're going to call this one hyphen. Y'all starting to feel what I'm cooking? Okay, so X is this most significant bit right here. We're going to kill this one. So that hyphen right there. Okay. That's X, Y, and Z. That hyphen right there is going to go to the 3rd bit. Right, like right there. Do what? Like we deleted them. Oh. Yeah. ROB hyphen. Are y'all starting to feel pretty powerful? I mean, we're basically making a typewriter right here. And all we got to do is learn some math and how to store stuff. And now we've got a computer. All right, so the hyphen button is going to go to the third bit. I start counting at the least significant bit, so that's going to be your first bit, and then on up, okay? Now, the R, well, let's work backwards. The second line is going to have an OR gate with O and B connected to it. The O and B is going to be on that OR gate, and it's going to go to the second, the middle one. And then there's going to be one more OR gate. It's going to go to that least significant bit. And it's going to have an R and a B on it. Okay. Now, whenever I ask you to save it, say yeah. And then if I go and push, I push the first button, I get a 1 out, but I also get the R in the decoded. You remember we put the 7 segment over here? That was already decoded for binary. All right, so I get a 0, but on our decoded part, I get an R out. I mean, to me, that's pretty powerful. You're encoding it, normally would store it somewhere. So I store a R, then I store an O, and then I store a B, and then I store a hyphen, then I store another B, right? I push O, I push B, push hyphen, B. Okay, if you put it in a truth table, you can make anything. All right. Like you might have 2 truth tables, one for the encoder, one for the decoder. All right. More than likely, you'd have other things in here. So I'd store a letter into a place in memory. And so I wouldn't know that 0001 was going to be. I'd have a different 0001. I'd have one for the program address, and then I'd have one for the encoded data. All right, so you've got data and you've got program address, which we'll start talking about in a minute. All right. Y'all got that? All right, let me show you what I mean. All right, so in a computer, a 4 could represent anything. Okay, it could represent a number, it could represent a letter, it could represent a color, it could represent anything. You know, you have to know how they encoded it to decode it, right? But eventually, we'll have something like, so we'll have a bunch of addresses, okay? And so I'll have a bunch of places in memory, okay? And let's say that they can store a 3-bit number, okay? So we have a storage area that can store whatever data we want in it, right? And would have a counter counting up. And every time I push the button, it would increment this. And then I'd tell it what I want to store in there, okay? This number over here is separate from this number over here. Like, there could be the same number in there. Like, I could store a 001 in there. But this would be like your program address, and this would be your data. Okay, so we're going to learn how to store a bit in a little bit, or like next week, okay? That data and that storage location, this is where it's located. Like, we'd have like 8 flip-flops, like memory locations. And then we would go through them sequentially and put the data we wanted in it, right? So I could have a keyboard with all the letters on there and have them all encoded, right? And then I could step through those memory locations and put that data into there so that whenever I play it back, I didn't hard code anything, right? Like, I went to a memory location, I pushed R, and then it stored 001 in there. Then I went to the next memory location, I decided to do S or B or O, right? And then whenever I play that back, it goes R, then the next letter that I put in, the next letter I put in. So now, like, I can hard code so that later on, I don't have to hard code everything, right? Like that, I can change things up at runtime. It's the difference between hardware and software. A GPU is hardware. It's doing all these ANDs. It's built with a bunch of NANDs, but ANDs, ORs, and NOTs, and it can do, you know, really big calculations at the speed of light near about. The processor, the CPU, is a sequential thing, okay? And so it's made of ANDs, ORs, and NOTs, but they're set up in a way like we're building. And then we would be able to go and change things at runtime. Like, we can code it to do other things, okay? By splitting up the hardware aspect of it and then the data that we're encoding. So this is just a preview to get your, you know, memory going, or your imagination going, okay? It's not something you got to really worry about yet, all right? But we made an encoder and a decoder, right? Have y'all read anything about multiplexers and demultiplexers? Okay, so copper's expensive. If we have a 64-bit processor, we don't want 64 wires coming out of it or going any long distance, all right? So what we can do is we can make something that would have a lot of inputs, and then it'd put out one output, okay? Imagine a telephone. So I've got a telephone over here. My grandma's got a telephone over here. Your mama's got a telephone over here. Dad's got a telephone over here. All right, so your mom told me not to call her, but she's okay with my grandma calling her, right? Now, think about all the combinations that we'd have to do if all of those were hardwired to each other, right? Now multiply that by thousands. So what happens is, like, we'll dump everything into like a trunk, and then it'll take that data and it'll put that data out on one line, okay? And then whenever it gets over to your neighborhood, boom, we got a demultiplexer to take it where it needs to go, okay? So we're dumping everything into one line, all right? Cool. So imagine I've got two peripherals here. And we've got a line over here, and I want to send it to one of two places. Okay? So I'd have a DMUX over here. I have a MUX over here. And now I can choose who I'm listening to and who I'm sending that data to. Okay? All right. So we're going to do a like a 4-to-1 MUX. Okay? We've got 4 things that want data out, and then we're going to have an output. And then we're going to have address lines. Okay? All right. So we're going to say that A0 is our least significant bit. So we're going to go A1, A0. What combinations can we have? 0, 0, 0, 1, 1, 0, 1, 1. Okay? So we're going to say Y is equal to data 0 right there. Y is equal to data 1 right there. Y is equal to data 2. Y is equal to data 3. Y'all follow? So depending on what address I put up here, this would, like, let's say I want to listen to whatever's happening on data 0. So I just change this address up here to 0, 0, and it's getting put out of Y. Okay? All right. So what we need to do is figure out how to make Y listen to each one of those channels at a time. Okay? So we've got Y over here. And it's going to be listening to either data 0, data 1, data 2, or data 3. Okay? All right. How do we make it so that this AND gate right here turns on to actually be listening to data 0? Zero, zero. I'm not going to draw 2 inverters, but y'all get the point, right? So if A0 is 0 and A1 is 0, then that turns on the AND, so D0 goes out. Cool? All right. For D1, that's when A1 is 0 and A0 is 1. Wait, A1 is 0 and A0 is 1, right? So A0 doesn't need an inverter. A1 does. Y'all follow? So now we're using those AND gates to selectively turn on when we have the address right, correct? All right, what about D2? A1 is 1 and A0 is 0. And then what do we need for this one? No inverters, right? Y'all follow how that's working? One of those AND gates, only one of them can be on at a time. All right, so we'll have A0 and A1 as addresses. And then now we can decide what information is going to be on that data line. Okay? All right. Now let's do the flip side of it, because I want to do both of these in deeds. Let's see if this works. That works, right? All right. So we're going to build a multiplexer. Let's build a demultiplexer, okay? So a demultiplexer, you're going to have your A0 and A1, and then it's going to have an input, and then it's going to feed it out to one of four different places, okay? So let's see if there's any kind of thing that works here. Let's do a truth table. All right, so we've got A1, A0. We've got 0, 0, 0, 1, 1, 0, and 1, 1. But now we've got four outputs. So we've got D0, D1, D2, D3. Y'all about to get excited because we kind of got a 2-for-1 deal here. All right. So when is D0 on? Only right here. Every other time it's off, right? When is D1 on? Right there. Every other time it's off. When is D2 on? Y'all follow? I might not have lined them up good. Let's do. All right, so D1. Cool. So now all we have to do is decide when D0 is on. And it's only on when A0 and A1 are both zeros. When is D1 on? When A1 is 0 and a 0 is 1. When is D2 on? The opposite of that. So 1, 0. And then when is D3 on? When both of those are on. That looks awful a lot like this, but without an OR gate, doesn't it? Yeah, like you're getting rid of the input, the extra input over there, and you're getting rid of the OR. Okay. Cool. A binary to decimal converter. Like the difference between that and a binary decimal decoder is D0 would be like an output instead of or that'd be where it ended, right? So would have like an LED there and then put a 0 there, so that when that LED showed up that we knew it was a 0. For the way that we're doing it here, well, okay, on a binary to decimal decoder, when you turned on D0, it was going to be on. On this one, when you turn on D0, it's whatever the input was. Oh, I did forget that input, didn't I? So this is an N. So we would have that input right there. So it'll pass through like all of those. Be right there. So with a binary decimal decoder, that D0 is going to be on as soon as 0, 0 is. On a demultiplexer, it could be on or off depending on what the input is. It's just like whenever you shift up to 0, 0, so D0 is active, it's going to be whatever's coming in this input. Okay? It'll make more sense when we do it in deeds. Okay? Y'all ready for deeds? I don't know about y'all, but I like deeds. All right. Make sure you've got this saved. And then you're going to do a new one. New circuit. I want to do an address. Okay? So go up here, put 2 input switches, rotate them. No, let's not do input switches. What I want to do, put an input dip switch and put a 4-bit input dip switch and turn it so that its legs are facing down. Mm-hmm. All right. Take 4 3-input AND gates. Okay. Take 4 input switches. Kind of line them up. For the first one, we need 2 inverters. For the next one, we need 0, 1. So we just need an inverter on A0. So we'll make that A0. On the second one, we need it for A1, so we'll put it right there. And the last one, we don't need any inverters. So all right, so 0, 0, 1. Hold up. I'm confused myself real quick. All right, so this one's going to be 0, 1. So this would need to go to that one right there. All right. This one would need to go there too. And this, yeah. Is that better? All right, and this bit right here is going to be connected to the middle one. All right, and all that gets fed into a 4-input OR gate. All right, now I want to see what's going on at the end of that. So we're going to take an output like an LED. Test LED. Put it right there. All right. Now, depending on what address I put it at, one of these is going to be able to control that output. Okay. When you save it to mux, dmux, last name, underscore last name. All right, so this button should be able to change that. This button shouldn't be able to do anything. This button shouldn't be able to do anything. Do what? Yeah. Now if I go to address 01, this one should be able to control that output. If I go to address 10, this one should do it. We go to 11. That is a multiplexer. That's how we can start routing stuff. Yep. My logo disappears. Do what? Mutz, dmutz, underscore your last name. I want to try something. Highlight, like, stop, once you stop, highlight all of this, do control copy, then control V. Let's put it way over here. Okay? That's the meat and potatoes of it anyway. Y'all got that? Get the AND gates and the actually do a control Z to undo that. And go ahead and drag, like, get all of this other than the OR gate. Control C, control V, and then put this way over here. All right. Now we're going to doctor this side up. Take the extra wire off the end of the ANDs. Just put test LEDs on each. Okay. Then go ahead and drag these switches. Well, that didn't work. Go ahead and delete those switches. You're going to tie them all together. All right. So you're going to come out of here. Yeah. All right, so highlight everything that you want to cut and do a Control C. So that'll copy it. And then you hit Control V and it's going to pop up and you can go and place it wherever. Okay, then do Control C. All right, and then do Control V. It's a paste. All right, now like move it to where you want and click it. Did it do it? All right, so off the end of the AND gates, put a test LED, then take all of the little input switches that we had and delete them, and then connect all of those to that output. Okay. Now, what'll happen is this side can dictate what's going on that line, and this side dictates where it's going to. Okay? All right, so once I run it, like I'm sending data over to that address. Okay? This is the address that it's reading from. This is the address it's writing to. Okay, so I can move that to any address that I want. All right, I'll go over here and change the read from address, and now I'm able to write onto that line. So this gets very important when you have hundreds of things that are all interconnected and you don't know where they're going at any one particular point, right? Because think about it like a highway. All right. instead of having a road to my grandma's house and a road to the store and a road and everybody having a separate road to get to places, you go from your carport to your driveway, and then you get on a small road, and then you get on a bigger road, and then, you know, like you, same way to get to my mama's is the same way you get to the casino, right? So now we can start routing stuff, okay? Yeah.
Same as circuit can be similar.
Um, there's probably a connection. That was 17. So okay. So that's the line that this should go to. Okay. So okay, so all right. So, this is going to go where those. Okay, so you're close, okay. Yeah. All right, so this right here is. All right. We got to put up some fine or something. Good Lord, that's hard to deal with, isn't it? All right, so I'll give y'all some time. Like, we got 20 minutes left, but I want to talk about this circuit, okay? We should start being able to think in terms of the data that's going to do stuff for us and like addresses, okay? So what this would represent would be like an address location, okay? And this would represent the data that we want in the address, or yeah. So if it's on or off, right? So I've got an address of where I want it to come from. So it's looking at this right here. And then I've got an address over here that's separate. and I can put that data, I can move that data through one wire, right? So imagine we've got 8 things. We've got 4 things over here and 4 things over here. How many combinations is that? 4 times 3 times 2. 24 combinations, right? Would have 24 different wires just to route those. Imagine we needed a house going from each one of those to each one of those, right? Would have 4 going to this one, and then would have those 4 going to this one, would have those 4 going to this one, would have those 4 going to this one. Okay. Four to here, 4 to here, 4 to here. My math was wrong. All right, so 4 times 4. It'd only be 16 different roads. Okay. But if we need to get this stuff around, like y'all see that that's an order of magnitude better, right? Because if we had 5 locations, then we'd need 25 wires to get all the different places that they could go. Okay. This is kind of the basis of what we use for serial to parallel and parallel to serial also. All right, so serial to parallel, we would clock in bits one at a time, load them up so that they're side by side, right? And then put that out. And the opposite for parallel to serial would load up, you know, let's say 4 bits, and then we'd clock them out one at a time. Okay. We didn't get to adders. I want you to read about half adders and full adders. What it comes down to, I'm going to give y'all 20 minutes to help each other get like this part done. But I want to give you some food for thought real quick, if that's okay with y'all. That's this right here is going to be the lab. So, huh? No, this is it. Like you're done. But I want y'all to read up on half adders and full adders real quick, right? Because we'll add those in for the next thing. That'll be one of the first things that we do. But I want you to think about 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. Okay? 0 plus 0 is 0. The sum of that is 0. 0 plus 1 is 1. 1 plus 0 is 1. Now, there's no room to put a 2 in one bit. So the answer to 1 plus 1 for the sum is 0. And then you've got what's called a carry out bit, which means that it's going over into another adder. Okay? Cool? What is this right here? That's an exclusive OR, right? Now we know how to make an exclusive OR, so let's say we've got A and B right here. A and B. Boom. We've got our sum, and then this carry out bit, we'll take the A and B, and what is it? It's 0, 0, 0, 1. It's an AND gate, right? So this is our carry out. We added 2 numbers. Okay? So if we had 0, 0 there, we'd get a 0 here and a 0 here. If we're adding a 1 plus a 0, we get a 1 here and a 0 here. And then if we have a 2, then there's nothing in that first spot. Right? but there's a carry out that's going to go over to the next place. This is called a half adder. And all I did was look at what it would actually be if I added those numbers together and made logic for it, right? So if I have 1 and 1, that answer would be a 0, and then I'd have a carry over here that I have to do. Okay? Cool? Now, the only thing, this is called a half adder because it cannot take care of that carry out. What we'll do is we need to add a carry in so that if we have a carry out on something, that we can add it together. Okay? So we just made a half adder, but when you're reading it, I hope it makes sense to you. Read the full adder until it does so that we don't have a whole lot, like we can kind of blow through it like we did this. Okay? Deal? And what I want y'all to think about too, look at adders and look at flip-flops, like memory location. Okay? Because what we want to do next is we want to be able to clock in a piece of data. So if we have a 1 right here and we clock it in, then it stays a 1 until we clock in another piece of data. Okay? So that's how we're going to start storing some of this information. Okay? But we're going to build it out of ands, ors, and nots. Cool? So those are 2 things I want you to read about for next time is half adders, full adders, and as much on flip-flops as you can. Okay? All right. Y'all can help each other get caught up.